In this video, we're going to talk about valence bond theory. Specifically, we're going to talk about coordination number 4 and the limitations of valence bond theory. If you're looking for coordination number 6 and an introduction to the valence bond theory in coordination compounds, there's another video on that. And in that video, we took 4 examples. In the interest of time, I'm just going to list down the examples one more time. And what did we have so far? We said that let's take 2 compounds of cobalt, 2 of nickel, and put different ligands on those, okay? The result of that was that they had a different magnetic moment and hence different number of unpaired electrons that you got from this equation. And we also figured out the charge on the central metal, which was the same in both of these, okay? So we're able to compare apples to apples. And then we figure out the shape and geometry and hybridization of these 2 of these. We're going to focus on these 2 right now. Okay, let's get started with NiCl4 2-. If you're wondering what happened with these 2, check out that video and we'll just summarize all of this towards the end of this as well. And then we'll wrap it up with the limitations. Okay, so nickel NiCl4 2-. This is the electronic configuration of the ground state of nickel. It's going to be argon 3d8 4s2. Now, what we're going to do is, the charge over here is 2+. So let's remove 2 electrons right away. Okay, let's do that. And this has 2 unpaired electrons, which gives the magnetic moment of 2.8. So looks like these are going to stick around. Okay, and what's going to happen next? I think you know what's going to happen. Hybridization, you've got a coordination number of 4. So 4s combines with 3 4p orbitals to give you sp3 hybrid orbitals. 4 of them. That's what these orange things are showing you. Okay. So, yeah, I think we're done here. This kind of tracks. Take a moment to recognize what's happening. 2 unpaired electrons, 2 unpaired electrons. Okay. I've circled them. 4 coordination number, 4 orbitals that are hybridized. Remember, hybridization is a mathematical concept. You are combining atomic orbitals, which means, you're adding up the wave functions. That's what all of this is. Although it's hypothetical, you're still able to describe the shape, geometry, and this spin idea by using this concept. Okay. So clearly what happens next is that this behaves as a Lewis base, these chloro ligands, donate electrons to nickel, these hybrid orbitals, which behaves like a Lewis acid, and you got 4 pairs of electrons from 4 chloride ions. Chlorido, if you like the naming of the way the naming works. So let's write that down. sp3 hybridized orbitals of Ni2+ are shown by this, and this forms a high spin complex. Why high spin? Well, it's got some value. Oh, it's 2.8 high. We'll see. I'll tell you why this is high. Wait for a moment. We'll see right away. This forms a tetrahedral complex. You've seen sp3 before in chemical bonding and you know that this is tetrahedral. So let's summarize all of that on a quick slide right over here. Okay. This is said to be paramagnetic because it gets attracted. These electrons, they align in a magnetic field. If you want to check out what's that about, what is magnetic moment about, check out magnetic susceptibility from grade 12 physics. Awesome video. This is the structure and look at that. We've figured this out. If you've checked out the previous video, let's not call it a previous, it's another video. It's another video on coordination number 6. You'll know that we identified that this is octahedral, both of these. This was D2sp3, this was sp3d2. If this seems unfamiliar, check that video out. But for now, in this video, we're going to focus on these two complexes. So this is sp3, which is what we've just figured out with 2 unpaired electrons. Let's look at the next one. NiCN4 2-. Yeah. For the sake of simplicity, I've taken the same charge. So we go through the motions. Let's remove these electrons. But something interesting you see right away. Look at this. They're unpaired electrons. But I mean, there are no unpaired electrons. Yeah, none. Which means that this is weird. This has unpaired electrons. So maybe some sort of pairing up happens. Sure. Let's get from Ni2+ to Ni. Ni to Ni2+, which is what we've done over here, argon 3d8. And next, I think these are going to pair up. And this is where things get interesting. You see what happened here? Instead of sp3 orbitals, now you've got you've got dsp2 orbitals. dsp2, yeah. Let's look at that one more time. You see that cool animation? Yeah. So this one d orbital, one s, and two of these p, that is what is combining. So you've got one 3d plus one 4s and two 4p orbitals combining, which gives me dsp2 hybrids. Ooh, that's interesting. Rest of it is very similar to what happened in NiCl4 2-. Why did I do this though? Because I know for a fact that they are zero unpaired orbitals, these zero unpaired electrons, and that makes sense if we do this. And then rest of it is all right. These cyanide ions, all of them give 4 pairs of electrons, and everyone's happy. These are dsp2 hybridized and orbitals of Ni2+, and this is a low spin complex. Now you see why I call this low spin and that high spin. This is pretty awesome, and you're able to see that, okay, this forms a square planar complex because it is dsp2. Yeah. And although we're celebrating this was a cause of concern as well for Valence Bond theory, because without doing all of this, you're going to be scratching your head saying, what's happening? Why is it square planar? Why not sp3? It just so happens to be that this is the only way you could explain this idea of zero unpaired electrons. And all we did was change the ligand. And that was a bit of a concern for VBT. We'll talk about that. This is diamagnetic. Okay. Why diamagnetic? Electrons are paired up. No unpaired electrons. And this is the structure. NiCN4 2-, and this right here is square planar. They're all in the same plane. So that is the summary of these two different compounds, these two complexes. Here is an outer orbital complex, the first one, NiCl4, which is high spin. And the next one we saw was a low spin complex. It is inner orbital. Why? Because inner 3d orbital takes part in this, and no d orbitals in this, just sp3. But hold on, does this mean that all sp3 complexes are high spin and all dsp are low spin? Why am I asking this question? Look at this. Let's go back here. Okay, sp3 happens to be high spin. Okay, dsp2 happens to be low spin. Can you make a general conclusion? I don't know. You tell me. Here's a compound. Here's a complex, NiCO4. It also happens to be a compound. Coordination number 4, monodendritic ligand. Charge on nickel, I'll give you this one. It's 0. Magnetic moment, hold your breath on this one. It's crazy. So figure out the hybridization. Pause the video here, figure out the hybridization, and tell me this. What's happening with this? Is it going to be a high spin sp3, low spin dsp2, or a third thing? Some food for thought. Okay, this was a summary from a different video. Let's summarize all of them together. Remember, hybrid orbitals, they don't actually exist. They're some mathematical manipulation, yeah, wave equations of atomic orbitals and all of that. We're quickly going to summarize the valence bond theory, and then we will go on to look at the limitations, which is important. We've done this before, but if you haven't seen that video, we'll do it one more time. The ligands act as Lewis bases. The metal or metal ion acts as a Lewis acid, accepts electrons. Where does it accept electrons? In the hybridized orbitals that are formed. Hybridization of what? N-1d, Ns, Np, dsp2. This is 4p, 4s, 3d. Okay. Ns, Np. In this case, in this video, it was only sp3, but you could also have 4d orbitals in the mix. That was going to be sp3d2 when you have a 6 coordination compound, 6 coordination number compound. Now this whole thing works because of overlap of hybrid and ligand orbitals, which we've also shown you. These are directional and equal strength bonds, and we're able to do all of this only because you measure the magnetic moment and then you backtrack that you must have these many unpaired electrons. So that must be the hybridization and which d orbitals are used. And that's the problem. You're doing too many things. There are too many assumptions over here. Okay, that was one of the biggest drawbacks. And there's no way for you to figure out what the magnetic data is, Why is it coming? What's this number coming from? You can make a hop, skip, and a jump is what we did and say that, okay, because this is a migratory data, so maybe this happens. But that failed when you had the same charge, same complex, but different ligands, same metal ion, but different ligands, right? In case of coordination number 6, we looked at cyanide, we looked at ammonia and fluorine. And in case of coordination number 4, we looked at cyanide and chlorine, right? That's weird. And this was, we didn't talk about this at all throughout this, but why on earth are coordination compounds colored? If something is colored, that means that there's some energy transition that's happening, right? That's what color is all about. You're able to see a wavelength that's reflected, something must be absorbed. Yeah, that's a bit of physics for you. Which means that there is no quantitative interpretation of thermodynamic or kinetic stabilities of coordination compounds. What? Yeah, look, energy, thermodynamics, kinetic, well, things stay there the way they are, they're very stable. You don't know any of this from VBT. Who's asking? You need to know this to be able to make reactions work with this. Sure, we are looking only at structures right now, but the goal is to be able to predict chemical properties as well. And you can't do that with VBT so far. And the last point that I told you, like, how do you know if something will be tetrahedral or square planar when coordination number is 4 without doing all of that? Yeah, just because the ligand is different? Yeah, and that was the last one. Some ligands are strong, some of them are weak. Strong, well, they bully the electrons to pair up, or weak, you're like, yeah, we are okay, it's all right if you don't pair up, and that's a problem. They weren't able to differentiate it. But if somebody told you that, hey, cyanide, Cn minus, is a strong ligand, and NH3 is also a strong ligand, then we can say that, yeah, maybe we could predict. But why are some ligands weak or strong? That was not explained. Yeah, I've given you a bit of extra information for crystal field theory, which is probably the next thing you're going to study. But anyway, I hope you enjoyed this. We've covered everything on coordination number 4 in this video and the limitations. If you want to check out coordination number 6 and the introduction, there's another video on that. Okay, see you around.